Hi everybody, today we are going to talk about limits, and this is just going to be a basic introduction, but this is certainly a concept that is absolutely fundamental to all of calculus. So let's start with the definition of a limit. So if your function f of x becomes arbitrarily close, essentially meaning it's just becoming very, very, very close, there's no specific degree of closeness, so to speak, but arbitrarily close to a unique number L, as x approaches c from either side, then it has what's called a limit. And this is how we write mathematically the symbol for a limit, and we read it as the limit of f of x as x approaches c is L. So you can see I kind of drew out just a simple function going like this. This is where x equals c. So essentially you're going to see what's happening as x approaches c from this side and as x approaches c from this side. And if they meet and converge upon a unique number, that y value is your limit. Now I do want to point out that f of c doesn't even need to exist for the limit to exist. So I'm not asking you what is f of c? What is your y value when x is c? I'm asking you what's happening as x approaches c. So there's a very big difference between those things. So once again, your function doesn't need to be defined at c to have a limit as it approaches c. But this is what we're going to be talking about finding today. Now, there are many different ways to find limits, and we're going to just talk about a few of the most basic ways, and we'll talk about more tomorrow. So one of the most basic ways to find a limit is by making a table of values and estimating that limit numerically. So we are going to be making tables of values using a graphing calculator, or you can do this on Desmos. This was generated with Desmos. So make sure that you are able to create a function and a table in your graphing calculator or on Desmos. But let's look at the function. It says the limit of 3x minus 2 as x approaches 2. So I'm wondering what's happening to my y values, which are right here, as x is getting really, really, really close to 2. So if you are going to use a table of values to estimate this numerically, we want to pick a couple of values that are smaller than 2 and then a couple of values that are bigger than 2. And by smaller than 2, I mean super, super, super close to 2, but still smaller. So look at how I kind of built up to it. I said 1.9, 1.99, 1.999. This is where 2 would be. And then we have a few values that are super close but a little bigger. So 2.001, 2.01, and 2.1. So these were the values for f of x that were generated. So you can see as we approach x equals 2, kind of going this way, and as we approach x equals 2 going this way, you can see that both of those are approaching f of x equals 4. So we can say that the limit of f of x as x approaches 2 is 4. So our table of values shows us that. All right, go ahead and pause the video and give this problem a try. So I used Desmos here, and remember we were trying to find the limit as x approaches 3, so I picked a few values smaller and a few values larger. So as I'm converging upon x equals 3, I can see that my y values are getting really, really, really close to negative 3. So that is going to be my limit. All right, let's try another one together. Here you might notice that we do have a function where if we substitute x equals 0, our denominator becomes 0, so our function is actually undefined. But remember, our function does not need to be defined at c to have a limit as x approaches c. So that's why we have to have other ways to find it rather than just substituting the value. So here we can see we have a few numbers that are smaller than c, or than 0, and a few numbers that are slightly larger. So as x is getting closer to 0 going this way, and as x is getting closer to 0 going this way, you can see that they are reaching the limit of 2. So the limit of f of x as x approaches 0 is 2. So essentially I'm asking, as x gets really close to 2, what's happening to my y values? All right, go ahead and pause the video and give this one a try. Okay, so here you can see I made another table of values using Desmos. So here we wanted to know the limit as x approaches 1, so a few values less than 1, a few values greater than 1, and as x approached 1 from either side, my values converged at 0.2, so that is our limit. Okay, so now let's talk about a different way to find a limit, and you can actually do it graphically. So you can use a graph to estimate a limit, and actually graphing calculators and Desmos, they have a trace function, so you can actually trace along your graph and it will tell you each coordinate, so you can see the coordinate as you get really, really close to your value and as you get really close to your value from the other side. But here, let's estimate this limit using our graph. So we want the limit as x approaches 1. So here is where x is equal to 1. You might notice that when x is equal to 1, our function is undefined, but remember, it doesn't matter. So as x is approaching 1 from the left, and as x is approaching 1 from the right, so kind of going down this way and going up this way, you can see that it is going to hit a limit, which is 2. So the limit of f of x as x approaches 1 is 2. So this is just a different way to estimate the limit. Okay, I'll go ahead and try to estimate this limit using a graph. All right, so here is a graph of that function. So you can see as x approaches 2 from the left and as x approaches 2 from the right, it's going to reach this unique point at y equals 7. So that is our limit. As x approaches 2, it is equal to 7. All right, let's try this one. For this one, we'll just graph it by hand. So here we have a piecewise function. So this says that our function is equal to 2. It's a constant function for all numbers except for when x is equal to 3. Now when x is equal to 3, f of x equals 0. So that's the only point that's different. So let's start with that bottom part of our piecewise. When x is 3, f of x is 0. And all of the other numbers for x, f of x is 2. So it just looks like this, except for right here, and then it keeps going. So the limit, as you can see, what's happening on the left? Oh, well, it's at 2. What's happening on the right? It's at 2. So even though at this point, your y value is 0, as we're approaching x equals 3, as we are approaching it, f of x is 2. So that is going to be our limit. So our limit as x approaches 3 of f of x equals 2. Which is this value right here. So remember, it doesn't actually matter what is happening at 3. I want to know what's happening as it approaches 3, and the y values are always going to be 2. All right, go ahead and pause the video and give this problem a try. So here, same idea, we have a piecewise function. F of x is -3 for all values except when x is 2. But still, our limit as x approaches 2 is still going to be -3 because that's what's happening as x is getting up to that point. Okay, now we're going to talk about limits that do not exist, and we're going to talk about 3 different cases. The first case is when you have different behavior on the left and right side of your function. So here's a good example, the limit as x approaches 0 of this function. So let's graph it out really quick. We're just going to kind of make a t-chart in our heads. So you might see that at x equals 0, this function is undefined, but that doesn't matter. We can still find a limit, or maybe we can still find a limit. So let's plug in x equals -3. If x equals -3, we have +3 over -3, which is -1. If you substitute -2, we end up with -1. If you substitute -1, we get -1. And it will be a constant function up until this up until you hit the y-axis where we have an open circle because our function is undefined when our denominator is 0. Now let's try plugging in some values on the right. If you plug in 3, we get 3 over positive 3. So now it's going to be positive 1. So we have positive 1 here, 2 over 2 is 1, 1 over 1 is 1, and it's going to keep going until it hits another open circle. So if you look at what's going on, let's see what's happening over here as x approaches 0. So we're going to do a little bit different notation here. The limit as x approaches 0 from the left, putting a little negative sign means from the left. Well, this limit is -1. All of these values are -1. But if you look at what's happening from the right, the limit as x approaches 0 from the right of this function is +1. All of these y values are +1. So whenever you have a scenario where the limit as x approaches your c value from the left, so 0 from the left, does not equal the limit as x approaches your c value from the right, whenever they are not equal, this limit does not exist. And that's because the left and the right hand behavior are not the same. So while they do have, there is a limit as it approaches from the left, the overall limit does not exist. All right, go ahead and pause the video and give this one a try. All right, so you can graph this one by once again making a little t-chart. So here, once again, the limit as our function, or as x approaches from the left, does not equal the limit as x approaches from the right. So the left and right hand behaviors are different. So therefore, the limit does not exist. Okay, now let's talk about another case where we might have a limit that does not exist. And this is when you have what's called unbounded behavior. Essentially, when your f of x value is going to approach positive or negative infinity as you approach your c value. So let's sketch a graph of 1 over x squared and see what's happening as x approaches 0. We know that x cannot equal 0 because the denominator would be undefined, but let's sketch a graph. So I know that when I divide by a really large number, I get a very small number. So as x gets really big, I know that my value is going to be very small. But when I divide by a very small number, my result is actually a really large number. So as I'm getting closer and closer to 0, my graph actually is going to go like this. So this is a rational function. Now, if I do the negative values, typically with rational functions, we have something that looks like this. But you'll notice that we have x squared in our denominator, which is making our values positive. So it's going to end up looking like this. So you can see as x approaches 0, our graph is just going up forever and ever and ever. Our graph is essentially approaching infinity. So we could even say the limit of x as x approaches 0 of f of x, well, it's approaching positive infinity. And something like this is unbounded. So we actually say that the limit does not exist because it will never converge upon a unique point. It will just keep going up forever and ever and ever. So this is unbounded behavior, and unbounded behavior has a limit that does not exist. All right, go ahead and pause the video and give this one a try. Okay, so this one, it looks the same except now it's flipped because of the negative. But once again, as x approaches 0, you can see that our at the f of x will just keep getting smaller and smaller and smaller. It will approach negative infinity, so this limit does not exist. It is unbounded. All right, the last case that we're going to talk about for limits that do not exist are when you have what's called oscillating behavior. So this, you get a really, really interesting looking graph. So this is the graph of the sine of 1 over x. So when you see something like this, and you could keep zooming in, this is called oscillating behavior. So essentially what's happening, as x approaches 0, which we know is undefined when x is 0, we're going to get this oscillation where you're just pretty much swapping from above to below to above to below over and over and over. And this will keep happening as you get infinitely close to 0. And in fact, it will never reach the point where they are converging upon a unique number. So when you have something like this, we call it oscillating behavior, and we say that the limit does not exist. You could also make a table of values for this function, and you'd see the same thing. You'll just keep getting the same numbers rotating positive to negative to positive to negative to positive to negative, no matter how infinitely close you get to 0. So once again, when you see something like this, that's oscillating behavior, and our limit does not exist. Okay, that is all for today. Thank you so much for watching.